Okay, so hello everyone. Welcome to Human Chemical Society. This is meeting 4, and today we'll be doing chromatography of plant pigments. So we've started prepping. So I'm just going to show you guys what's going on right now. So today we'll be using beetroot. We're trying to extract the pigments from the beetroot as well as Kalalu. And here we have Kasha, our CEO, Chief Experimental Officer, and we have Tiffany, our Second Vice President. So we'll start to prep the beetroot. We've added a solvent to it. I believe we added ethyl acetate to it and methanol 50-50 ratio. Um, and we tried to get the surface area, increase the surface area. So we're putting it up or getting it as small as possible. So kind of like grinding it out so that we can get to the pigment. So as you can see, we're using just a little bit because you just need a very small amount. So we're going to use this capillary tool to apply it. So you just need a very small amount to add to the plate to do the extraction and the separation. Right, so this is our setup. Today we'll be using TLC, that's thin layer chromatography, and these are the plates that we'll be using. They're pretty small, not big. And this is the chamber that we'll be using to do the separation of the pigments. So we're still at extraction stage. That's the update. So once we get the pigment, the liquid part of this, so we'll add some more solvent to this one to get the liquid from it. And then once we get a concentrated liquid, then we can add just a drop, more like a dot. You're putting more like a dot onto the plate. Right here, where we call the baseline. So we're gonna put it at that line on the plate and put it within the chamber with some solvent and allow the solvent to move the plate. So we do have a presentation with the theory of how the whole process works. So while we're trying to get the solution or the mixture that we're going to use for the separation, we're gonna go to the presentation. Okay, guys. All right, so right here, we've just added one small drop of the extract. So just from that tiny bit, we don't need a lot. Added one small drop to it right at the baseline, as I said. And then we're going to do the same thing for the beetroot. So we've done the same thing for the beetroot there. All right, great. All right, so what we're doing here is to add the thin layer chromatography. We're adding the plate to the chamber. That liquid you see there is our solvent that we'll be using. And essentially, we're allowing the solvent to move up the plate. And as it moves up the plate, then it's going to separate our pigments. So the solvent that we're using is 50-50 of hexane and methanol. So basically half and half ratio of hexane to methanol. And we're covering the chamber to allow it to become saturated so that the solvent can properly move up the plate. So this is not going to take a very long time because as you see the solvent is moving pretty fast up the plate. And as you can see, the pigment is actually moving with it. Well, it's moving at different speeds for the two different pigments. But if you look close, right, so that's a closer look. You can see the pigment moving up the plate, right? The one for the beetroot obviously is moving up faster and farther up the plate than the one for the callaloo. And that would be because the components, the pigments within the two different plants are different, right? So the properties are different. How they dissolve in the solvent is going to be different. And of course, the pigment that is more soluble in the solvent is going to move along with the solvent and move at a faster rate up the plate and farther up the plate as well. Right? So you're just gonna give it a few minutes until it reaches almost up to that pencil mark there. While we're doing that, we'll just go through a little bit of the theory and yeah. All right, so for chromatography, right? Chromatography is an analytical technique that we use to separate our substances into individual constituents. So obviously the mixture that we would have obtained from the plant has several compounds within it. So we're using the chromatography to separate that mixture into the individual components, right? So for our chromatography, how it really works, we're working with a stationary and a mobile phase. So particularly for TLC, your stationary phase is the plate itself. That little white plate that we use, that's your stationary phase. Your mobile phase would be the 50-50 hexane and methanol solvent that we are using within the chamber. So if a molecule has a high affinity for your mobile phase, it's going to separate to a greater degree because it's going to move along with that mobile phase up the plate, right? And of course, if the affinity is lower, then it's not going to move as fast up the plate or as far up the plate. So you have several different types of chromatography, as we may have alluded to, but today we're utilizing specifically thin layer chromatography Something simpler that you guys may have done in high school would have been paper chromatography, where you can use it to separate stuff like pen ink or whatever ink is within markers. You can use paper chromatography to do that. And we will be uploading material and apparatus for a home experiment too, for you guys to actually do that at home. So you can um, run that experiment at home. Of course, it's not going to be as efficient as if you did it in the lab, but nonetheless, you can experiment with that at home. All right, so for plant pigments that we talk about, these are the chemicals within the plants that are able to absorb and reflect a particular range of wavelengths of visible light. So we already know we have our visible light spectrum, RGB, red, orange, yellow, green, blue, indigo, violet. And of course, the different colors are of different wavelengths. So the leaves of the plants contain different pigments because we know that plants utilize energy in the process of photosynthesis as well as in other processes. But you will find some major pigments such as chlorophyll A, chlorophyll B, carotenoids, and xanthophylls in high concentration within photosynthesized plants. So TLC, as I said, the solid your phase, your solid phase that you're utilizing is the TLC plate. And this is really a plate with silica gel, sometimes alumina, but one that we're using is silica gel is coated over the plate. It's very thin, breaks really easily. And our mobile phase is our solvent, of course, that we use that moves up the plate, travels up the plate. And our pigment, as I would have showed you, you just dot the pigment, just a small dot, you don't need a lot, onto the plate, and then it will separate into the constituents or the components based on the structure properties of the different components. Then it's going to just separate um, based on their affinity to the solvent. What we expect is that our chlorophyll B, which is usually of high concentration in plants, will travel the least distance with a mobile phase as it is more polar than the other pigments. And of course, we're using 50 a 50-50 ratio of methanol and hexane is nonpolar. So you would expect that pigments or compounds that are more nonpolar have a higher affinity for the hexane compared to the chlorophyll B. So chlorophyll B is a bit more polar, and so it will stay, maybe not stationary, but it won't move too far up the plate, right? The remaining pigments will travel a greater distance than chlorophyll B, um, beginning with chlorophyll A, followed by xanthophyll and carotene. So carotene is most nonpolar of the pigments, and so it will adhere or attract more strongly, or most strongly rather, to the mobile phase, and so travel the greatest distance. And once you get back to the experiment, you're going to see that. So this is what our results are going to look like. So we're going to go back to the experiment now to see what the results are looking like. And maybe we can deduce from that what we have. Visual finish.
Yeah, yeah, it's pretty much.
Yeah. So here we go. So it looks very pale in the tank, and that's because the pigments have separated out, so it doesn't look as concentrated again, but I'm sure you can see the streak of the pigment moving up the plate. So we're just removing the plates from the chamber. This is what they look like. So of course this one is the one that we took from the beetroot. And this one is one from the color. You can still see the color a bit in it. Just the same. And this is the third one from the color. Let's just do a little comparison. So this is our beetroot here. We did two color ones. Well, I am misinformed. My chief experimental officer and second vice president are correcting me. This one is the spinach, right? And this one is callaloo. And this one is the beetroot. There we go. All right. So as you can see for the spinach and callaloo, I wouldn't say the spots are at the same distance, but around the same distance. So it kind of indicates that that might be the same pigment. And of course, the color would give you an idea as well. And this here is our beetroot sample. So it hadn't traveled as far up the plate. And we don't see a distinct spot on the plate as we see for these two, right? So we can maybe make some kind of inference, maybe not a conclusion, but an inference that these might be the same thing. And of course, we know that this one is different compound. All right, so right now we're using a UV lamp to actually visualize some of the pigments.
So a few of them are UV. The ones that come up are UV. The others are.
Okay, so the ones that you can see with the UV light would be UV active, and whatever you can't see are not UV active. So UV active would mean they are able to absorb UV light or UV radiation rather.
The spray the reagent and the need to use.
Okay, so now we are going to use a visualizing agent. We're going to spray the visualizing agent onto the plate so that we can see the spots a bit more clearer, so that it can be a bit more brighter. So we're seeing the spots, but we can increase the visualization of it. So we're going to move to the fume hood, where we have to use the visualizing agent. We're just gonna spray it on it so that we can see the spot a bit better. Woo! The breeze is trying to take away the place. All right, we're back. So we're going to be moving to the fume hood in a second. And for those who don't know what a fume hood looks like, I will just show you guys in a bit. So these are what our plates look like. All right, so these are some pigments. Right now, you can call them standards. They're already pre-prepared in the lab. And as you can see, there's an NMR absorbance for each of them. That's the nuclear magnetic resonance. So these are a variety of pigments actually, and we're going to use carotenoids. So we're going to add it to our TLC plate. As I said, you can use this pretty much as standards because they've already been analyzed and everything. So yeah. So
Very fine.
this is the carotenoids. So we're trying to get a bit of it into the capillary tube in order to add to plate. That was a lot. That was a big drop. And guys, usually you don't want your spot to be too concentrated because you want an efficient separation or you want good resolution, right? You want to see the spots, right? So we're gonna run these in a chamber. This one is which one is it?
That one is spinach. Sorry, that one is together.
This is a spinach, beetroot, callaloo, and then we're adding it to compare it to the standard of the carotenoid. Okay? Yeah, so we're just gonna run this one.
It looks like it's
Here, adding it to the chamber with the solvent, and we cover the chamber. As you can see, the solvent is moving pretty quickly up the plate. So the TLC really doesn't take a long time to do. I'll just bring it closer for you guys. TLC don't take a lot of time. You're really not supposed to move it like that because you don't want to disturb the movement of the solvent. But yeah, so we're going to move over to the fume hood to show you guys how we add the TLC visualizing agents to the plate.
All right, so essentially a fume is a cabinet in the lab that you carry out reactions. A lot of these reactions is fumes that you don't want to inhale. So the fume hood essentially carries away the toxic fumes. By the in here, and there's a vacuum. You can hear it. There's a vacuum that actually pulls up fumes and transports it to the atmosphere. So we use it to carry out our reaction. Now this is ammonium molybdate. We use it in natural product isolation when we want to extract natural products from plants. And a lot of the times it's very difficult to actually see them when we carry out the TLC, so we use this as a visualizing. So we spray it on the TLC plate. Once it evaporates, you see the spots brighten, essentially. So I'm going to do that right now. I have to turn on the fume hood because if I should spray this without the fume hood, it has sulfuric acid in there, so it will irritate the eyes and you know. Once it's sprayed, we just use the heat gun to evaporate. it will take about a minute or so to get it to evaporate. You can see it drying, and then afterwards the spot will start coming up a bit bright. So around so you can see that something very polar was actually down there. So which one was this? Which one was this one over here? So it seems that it's finished has three compounds in there. One that is really polar and two that are not so polar. I guess this right here is one main compound. Show the thing. Well, it's like two compounds. We have one here. Three. Yeah, there's one at the bottom. Yeah. You see one, definitely one here. One picture up there. This one, there is two here in the shadow. Yeah. It seems as if there's one at the top, one in the middle that kind of tilted a bit, and then I'm seeing a little bit of shadow here. So there might be another compound here, but it's just that it's in such a low concentration that it's not showing up as bright as the others. Right? So it might be three compounds up there. If the spot was a bit tinier, the resolution would have been better. It would have separated a bit better. Well, I have some other pictures of TLC. I could send them in the chat. Okay.
All right, guys, so we've completed the visualization. So as you can see, versus when we just ran the TLC, you can see the spots really clearly right now. Versus when we just ran it, they were kind of faint, you couldn't see them so clearly. And so they're really bright now. And as Ricardo would have said, the smaller your spot, the lower the concentration of the pigment, and so the better they're separating. So you have a higher resolution, meaning you can see the spots more clearly. And you can see more individual spots. Right? So we had run another TLC, so we're gonna just quickly do that one as well and show you guys. Alright, so we're moving back to the experiment table, and essentially, when you have done your separation, what you're going to do next is your analysis. You're going to try to figure out, okay, what pigments am I looking at? Based on how far they move up the plate relative to each other. What is the pigment that I'm looking at? And possibly you may want to isolate it. You may want to do other things with your pigments depending on what you're experimenting on and what you're doing in the lab. But basically, that is pretty much the essence of the TLC. You're really separating the pigments. And of course, as I said, the smaller the drop, the less concentration and the higher the resolution. So the better you would see. So it wouldn't look as cloudy. You wouldn't maybe see spots grouping up at one spot or at one point. So you can see them more individually, more clearly. So yeah, we're going to move back to the experiment table to show you the other TLC that we ran in the meantime. So here we go. Let me show you. So here is the TLC that we did. So I think we did the carotenoids over here. Yeah, so this is the carotenoids. This was the beetroot, and this was callaloo. Yeah. So okay. So we can't see the carotenoids. So this is really the spinach. The green spot here. This red spot is the beetroot, and this one is the callaloo. Right? So the carotenoids, remember we had put it over to the far right, but we can't see it right now. So we're going to use the UV lamp to look at UV active compounds. All right, here. I'm sure we're seeing that little space right there where we had put the carotenoids. So they can move up to here. So now we see the purpose of the UV lamp. So we couldn't see it in the visible light, so we're utilizing UV radiation to visualize. You know, that looks a bit brighter. Yep, in essence. So there we go. And of course, as we said, the next step we would have done was to add the visualizing agent on the fume hood, and then we would see these spots brighter as we did with these ones right here. So basically, yeah. So they're pretty bright. It looks almost like ink. We could hardly see them before. All right. And TLC, it does give you a better resolution when you compare it. If it has a higher efficiency, you'd say, than paper chromatography, because we could use paper chromatography to do the separation as well. So instead of the TLC plate, we'd be using paper, so we could use a strip of this to do it. But the resolution would be lower. The TLC is actually higher resolution or more efficient than the paper chromatography. Yeah. Okay, so that was pretty much the experiment for today, the TLC chromatography of plant pigments. So we had used the beetroot and um, the beetroot, the spinach, and callaloo. Very nice. All right, so these are some paper chromatographies done at home.
The third one, the planted one. This one is carrot, very brown.
So these are plant pigments. All right. So these ones are done at home, right? Let me show you. So you can see these are paper chromatography that you can run at home. We'll be sending you guys the experiment for that. But as you can see, it's lower resolution. You can see the streak of the movement of the pigment right there, but resolution is not very high, right? And there's not a lot of separation. We're going to add UV light to it to visualize. So you can see it's a bit clearer under the UV lamp. Which one was the carrot? This one? So it's better seen under the UV lamp, but still compared to the TLC, you can definitely tell that TLC is more efficient, yeah? And also when you're doing it at home, the reagents, the material that you're using, it's not up to standard. I wouldn't say it's not up to standard, but the quality of it is not as high as what you would use in the lab. Also the concentration, for example, your alcohol that you'd be using as a solvent, the concentration is really not as high as what you would use in the lab. So the separation, you wouldn't see a lot of separation compared to what we do in the lab, but you would definitely see some movement. And of course, we know that the chromatography really can be done with any colored pigments. So as I would have said earlier, I'm pretty sure persons did this in high school with pen ink or markers. So that can be easily done at home. Yeah, so that's pretty much it. Do have some questions for you guys. Because remember, we have a leaderboard right now. I do believe that Joffin is still leading points wise. Not sure if Joffin is here, but I'm pretty sure she's leading points wise. So we have questions for you guys. We have trivia. You must learn something today. So we're just going to quiz your knowledge. So we're going to bring back up our presentation. We're going to see how much you are paying attention, how much you understand, how much you learned, and you can get some points, right? So moving to our question. Do I see Joffin? I see Brant here. go into the questions. So this is just a synopsis of how we would have expected the results, and we showed you live how we got the results and what the chromatogram looks like. All right, the question time, as I said. And we already know the protocol. First person with the correct answer gets the point. And for persons who don't have any points as yet, you get a chance to be added to the leaderboard. And let's see who makes it to the top of the board by the end of the semester. All right. So let's go to question 1. What is chromatography used for? Easy question. Easy question. What is chromatography used for? First person with the correct answer. Easy question. Do we have an answer? Anybody? You think your answer is right? What you think? Miguel says C. Is Miguel correct? Do you know? That's the correct answer. So Miguel gets the point. Miguel gets the point. Miguel gets the point. Stephanie, why you doubt yourself? Why did you doubt yourself? Miguel gets the point. You use it to determine the constituents in a mixture and to determine analyte concentration. Right? So obviously, the more concentrated a compound is in the mixture, then a brighter spot. You're gonna get a brighter spot, right? Or a clearer spot. So let's go to the next question. Miguel gets that point. Which of these is false? Which of these is false? Is it that A, paper chromatography has a liquid mobile phase? B, high performance liquid chromatography has a solid mobile phase? Or gas chromatography has gaseous mobile phase? That's the correct answer, people. Are we sure? Jazan got that one. Jazan was quick on the ball with that one. Jazan was quick on the ball with that one. Yeah. So AHPLC does not have a solid mobile phase, people. We definitely know that paper chromatography has a liquid mobile phase. And we know that our gas chromatography has a gaseous mobile phase. So Jazan, you get that point. Third question. Question number 3. Which one of these is not a chromatographic method? Pseudo-affinity, molecular sieve, or derivative? What's the answer, people? Which of these is not a chromatographic method? How about I go Google it now? No. Don't find that. Quick and fast. So far, Miguel has a point. Jazan got a point. Miguel says C, and that's correct. Jazan, you can't answer the question like you're asking me. You have to tell me the answer. So Miguel gets the point because he said C first. Yeah, so he gets it right. So number 4, we're at number 4. Number 4. Yeah, man, Josan, you can't. I asked you the question, you asked me back a question. You can't ask me a question. You have to give me the answer. Number 4. What pigment traveled furthest on the paper in the experiment? We talked about this. We talked about. Ah, are you sure? Are you sure that's the answer? Jason, are you sure? Okay. So you are correct. You are correct. You are correct, Jason. It is the carrot. It's really carotenoids, but yes, you are correct because it is most non-polar. That's what we said, right? And we said the chlorophyll B was the most polar. Yeah, we did say that. So Jason upon 2 points, don't I believe so. Jason is on 2 and Miguel is on 2. And for our last question, our final question for today, let's see who gets the points. What pigment traveled the least on the paper in the experiment? What traveled the least? C. Jason gets it. No, Stephanie, come on. I just telling the answer now. Literally just telling the answer. Jason got it. It's C, guys. So Jason has gotten, or Stephanie, that was a horrible mistake. But Jason got the answer. So Jason got 3 of the answers, and I think Miguel got 2, right? Yeah. Miguel got 2, Jason got 3. And we already know that for each point you get in the activity, you get 10 points. That's 5 plus 5, 10. That's 2 times 5, 10. That's 9 plus 1, 10 points on the leaderboard. So Jason has got 30 points today, and Miguel has gotten 20 points today. Yeah? Jophine, what's happening? Jophine, what's happening? Jophine is leading right now, but it's looking sticky right now, Jophine. It's looking real sticky right now. But that's it for today, guys. That's it for our experiment. Thank you guys for joining us. Thank you for coming out, and of course, the video will always be here for you guys to come back and watch. Um, Jophine is distracted today, and that's okay. Maybe it's one of them days. Remember to sign up to become a member. The membership form is in the description, as well as the meeting registration form is in the description to show that you attended this meeting today. And follow us on Instagram, of course, at UWI ChemSoc. Subscribe to our YouTube page, like, comment, share, subscribe, and all of them good things. All of them good things. And we will see you guys next week. And until then, we say experiment with a chemist and you will love the reaction. Bye, guys. We'll see you next week.